a few things before we start here today. Number one, the trace evaluations. I mentioned this already. How many people have done those? Okay, thank you very much. That's I encourage everyone to do those. It's useful for me and useful for the people who take the class next time. Usually this board is not. Get out. So what do we have? What's the current homework? The last one, 13? Is that right? 30. Yeah, 13. We have a final exam. That's Saturday, right? Is it the 20th, 21? And there is an online system for checking grades. Have we seen those grades? Is anybody who tried to see the grades but they can't? Okay. There is a CCIS portal that you have to put your CCIS credentials first, I think. What?
The page is coming blank.
The what?
The page is blank for me.
So after you pass the CCIS portal. Okay, there might be a typo in the grade sheet, like if your name is not spelled correctly, then that you can easily ask the TAs to show you directly in the grade sheet what's going on. Or at office hours we can debug it together. Since everybody can see them, this is probably a small typo.
Caps in
ID or caps or something, that there could be something. Those are the grades that we have. So I want you to check them before we compute final grades based on those. Okay, so what we want to do today is to talk about the RSA crypto system. That's a topic in itself, just like last time. So how many people have studied RSA, the crypto system? Hands up. Do we know how it works then? All right.
maybe.
So we'll do a recap. We'll go much faster than at the undergraduate level because we don't have a lecture about that. This is more mathematical in nature than other things, but the mathematics is not complicated. So it's not like you're going to struggle with this math. You're not. But then how to implement such a system in an efficient way, that's a little tricky. Okay? So let's review how this goes. First of all, so RSA So we need first some preliminaries about this. B equal 19, it's a prime number. Or simply a prime. Because, why? The only numbers that, integers that divide 19 are 1 and 19. No? So if A is a natural number that A divides 19, that implies A must be in the set 1 or 19. There is no other number that divides it. So that's a well-known thing since we were little kids, right? Now, if I so any numbers n, it's a natural number, decomposes uniquely into primes. For example, if n is 12, that is 2 times 2 times 3, that is, we say 2 to the 2 times 3. And if n is 48, that is 2 to the 4 times 3. And if n is 50, then that is 2 to the 5 squared. Please observe that all these numbers here are primes at some power, right? If n is 1452, that is 2 to the 2 times 3 times 11 squared. Okay. Decomposition into prime is a unique thing. And then, let's add one more here. This is 2 squared times 3 squared. Now, if I want to compute the GCD, stands for what? Greatest common divisor between two numbers. I'm going to take 48 and 36. 48 and 36. I write them as prime decompositions. So 48 is what? 2 fourths to the 3. 2 fourths times 2 to the 4 times 3. And 36 is 2 to the 2 times 3 to the 2. So the way I get the GCD of those two things is to look at the prime factors and pick the most that are in common. So how many 2's are in common? One has 2 2's and one has 4 2's. So how many are in common? 2 2's. And I look at the 3's and I say how many are in common? 1 3. Is that true? 2 squared times 3 is how much? 12. Is that the GCD between 48 and 36? How do I check this? 48 is 12, the GCD, times 4, and 36 is the GCD times 3. I can see that this is the highest divisor simply because the remaining ones, I have no prime factors left. So we say GCD of the 4 and 3 is 1, meaning no prime factors in common. This is also called, when people say coprime. Two numbers are coprime. Doesn't mean they are prime. Like 4 is not a prime number. It just says 4 and 3 are two relatively prime. Doesn't mean they are prime. It just means they have no primes in common. Okay? Let's take another example. Here. GCD of 60, which is 2 to the 2 times 3 times 5, and 50, which is 2 to the 2 times 5 to the 2, is going to be what? Same thing. Common primes, 2 squared times 5, which is 20.
That's 2 into 5. 250 is 250.
10. Right? Because 60 is 6 times 10, 50 is 5 times 10, 6 and 5 are coprimes, right? GCD of 6 and 5 is 1, they are coprimes. They have no common primes. So that's the GCD and the primes. And there is an algorithm for finding the GCD, right, between two numbers. So the Euclid algorithm for GCD, that's how we find the GCD. So you can decompose the number into primes and take the common primes like we did here. Why is that not a good idea at scale if those numbers are really big? Theoretically, I can still decompose them into primes, take the common primes to the product, that's the GCD, but why is that not a good idea? Why can't I do this for really big numbers? What's the holding me down? Factorization or decomposition, it's a well-known hard problem, right? So let's make this observation here. N equal P1 times P2 times Pk factorization is a difficult problem. In fact, a lot of things in real world, not just in theory, relies on this fact. Bank cryptography, for example, relies on this mathematical property. The factorization, it's a hard problem. If I give you a big, big number, it's not easy to get the factors out of it. We are not 100% sure this is true. We think it's true. We're not absolutely sure. So in fact, in a common sense, in a business sense, we are sure it's true because so many smart people try to figure it out and they fail. But we're not absolutely mathematically sure. So it is a theoretical chance, there is there, that somebody very smart, very creative, comes up with a way to do factorization 10 years from now, and it's very efficient, and you can factorize any big number right away. That will cause enormous problems for the world economy. So we think that's not possible. In fact, everyone, including governments and weapon systems and all that, relies on this fact that we believe factorization is hard to solve efficiently. Now, of course, we can solve it non-efficiently, like trying out factors and see what divides what. There's even faster methods to do that. But nothing is like on really big numbers, nothing is easy to do. There's no factorization quickly. And we think that has to do with the nature of natural numbers or integer numbers. It's not a matter that we don't know how to do it. We don't think it's possible. I don't want to talk about quantum computing, but there is a possibility that if quantum computing ever becomes a thing, then some problems like that might become easier, not because they're easier, but because quantum computing has the theoretical possibility of solving a lot of problems simultaneously. So that just complexity of what we can solve, it would increase. But we're not there yet. So I'm going to present a version here that's called extended. Because we don't want just the GCD. Between 50 and 60, or between, what did we do here? 48 and 36. We want not just the GCD, we want to produce the GCD, of course, and we want the GCD coefficients. So GCD coefficients are two numbers, let's call them X and Y. So we have the input A and B, right, just like before. And we not just want the GCD, we want this X and Y such that the GCD of AB is A times X plus B times Y. So given A and B, who has A and B here? 60 and 50. We got that GCD, 10. But we want a little more. We want two integers, X and Y, that have this property. This is sometimes called Bezout equation. I don't like the name, but if you read it somewhere, they might say Bezout equation. So X and Y's are integers. So first of all, is that even possible all the time? Like, what are the coefficients that we would need? 60 times x, who's x? Plus 50 times y, who's y? How can I get this to be 10? Right, 10 is the GCD. Why would I need to put integers in x and y here?
So 1 y minus
1, and the other one would be minus 1. That works. How about on 46 and 48 and 36? Same thing, right? 48 plus times 1 plus 36 times minus 1 will be 12. That doesn't mean they're always 1 and minus 1. And they're not unique. Even here, I could come up with some other numbers than 1 and minus 1. Anybody can give me another possible x and y, not 1 and minus 1? How about if I put here minus 4? So x and y are not unique. And we're not picky on which one we're going to find. We're going to find some x and y. Okay? So how this goes? Here's what we're going to do. We're going to rely on an equation that says A is B times Q plus R. This is the integer division. Let me write integer. Q is quotient. And R is called so Q is an integer, right? Can it be negative? Yeah. And R is in what set? I'm going to assume here that B is a positive number, at least 2. So the remainder, when I divide by B, this is A divided by B. Where is the remainder? What are the possibilities for the remainder? 0, 1, 2, up to B minus 1. Right. So if I divided 25, I get the reminders from 0 to 24. And we can say this, the reminder sometimes we say A is R modulo B. That says that the reminder or the two numbers A and R have the same reminder modulo B. Sometimes we write three lines here. Some books do that. It's okay. So this mod operation takes the reminder, right? So we can say, for example, in terms of mod operations, 60 let me see, 70 equal 50 modulo 20, is that true? Because they are equal with 10. The remainder of both 70 and 50, when I divide by 20, is 10. That's why they're equal modulo 20. Maybe I can add 3 lines. Some books use 3 lines in here. Modulo operations, right? And not just that. I could say modulo operations 25 times, let me see, 17 modulo 10, it turns out I can take the modulo before the multiplications. I can say that's 25 modulo 10 times 17 modulo 10, everything modulo 10. So how much is 25 modulo 10? 5 times 7 modulo 10, so that is 5. Same thing with multiplications, right? Let's say 11 at power 4 modulo 8. That is 11 modulo 8 at power 4 modulo 8. So now how much is 11 mod 8? 3 at power 4 mod 8. So how much is 3 at the 4? 81 modulo 8. So I can do this kind of modulo operations. Right? There's a multiplication, addition of course works, right? Like 25 plus 17 modulo 10. I could do 25 mod 10 plus 17 mod 10, everything mod 10. 25 mod 10 is 5, 17 mod 10 is 7. That's 5 plus 7 mod 10, which is 5 plus 7 is 12, modulo 10 is 12. So modulo operations work as you would expect. Okay, back to here when I have this reminder. These, if I do these things this way, Q and R are unique. So if I force R to be the reminder, there is only one Q and one R that have this property, and they always exist. So here's what we're gonna do. We're gonna present this algorithm little by little. So we're gonna say like A, we start with A equal, for example, 51. With B equal 9, that's an example here. I want the GCD of 51 and 9. And I'm going to compute the quotient, so the extended algorithm has to do with repeated division. So I get the quotient, I get the reminder, and then maybe write it this way, Q here, and R, and then I'm gonna make them X and Y. So we'll see how this table goes. So when I divide 51 by 9, what quotient the reminder I get? And the reminder is? 6. I leave the X and Y for now alone, but I move, and my next, if I keep going dividing, anybody remembers who's my next A, who's my next B? In the extended Euclid algorithm, or in the Euclid algorithm? A is the previous B, and B is the previous R. That's how this algorithm goes. It keeps going down. A was whatever B was before, and B is whatever R was before. So what's my new quotient now? We can call this Q1 R1, and this is Q2 R2 now. Who's my quotient now? 1. And the remainder? 3. And I'm going to have an X2, Y2 here. Now, who's my A now? 6. Who's my B now? Where is this coming from? It's coming from here. And this is equal 6, coming from here. Who's my quotient now? This is Q3, because I'm on line 3. Who's my quotient now? 2, what's my reminder now? 0, x, and y. So what happens if r equals 0? Stop. I stop when I get no reminder. And the GCD is right here. Sorry, the GCD is right here. The last thing I divided with when I got a 0, b, that's the GCD. How many people remember this algorithm from high school, secondary school? When did it happen? At some point it happened, right? Right? Yeah. How many people remember that? Nobody. We didn't do number theory in secondary school and high school. That's true. Different countries do different things. You'll be surprised. Some people do in secondary school probabilities and statistics, but no number theory. Others do number theory and combinatorics, but they don't reach probabilities until college. So different countries have, same thing with calculus. Some people do calculus, some people don't do calculus until college. So that's okay. This arithmetic is very simple. They can be easily presented at 7th grade level. It's nothing complicated. So GCD is the last B that I have when I got the 0. And you can easily see that. The GCD between 51 is 3 times 17. 9 is 3 times 3. So the common prime will be 3. Okay? So that's when I stop, and I've got my GCD right here. But I need now to go backwards and compute x and y. When I stop, it's very easy. What coefficients? So the equations I need is a times x, right? Plus b times y has to be the GCD. Right? That's what I want. I want a times this x plus b. Who's a? 6, right? Times whatever x is plus b, that's 3, times whatever this is, this x and y value. They have to be the GCD, but the GCD is 3. Because GCD is exactly this b. So there's an obvious x and y that works because this b, so this is ax plus by is the GCD, right? I think it's obvious that 1 and 0 are going to work here. Because b is the GCD, so b is both here and here. So then if I put 0 and 1, bingo, I got it. That's not, again, the only ones. 0 and 1 was just the easiest ones to put here. And they only work at the very end. When I divide with b and I get r0, to satisfy this equation, ax plus by is the GCD, I can just put 0 and 1. Okay? We following that? That's always true at the last line of the algorithm. When I got, because I know I've got reminder 0, that's why I stopped. When I got the reminder 0, I need a times some coefficient plus b times a coefficient to be equal b. So the obvious coefficients are 0 and 1. That's going to give me b. Not the only ones. But the question is, now that I've got this x and y, 0 and 1, how do I move in here? In here, I need what equation? 9 times this value, right? Because now a is 9 in here, plus b times this value, that's 6 times this value, equal, the GCD is the same. GCD remains the same all over the place. So the GCD is still going to be 3, like in here. I'm going backwards now. So for this Q and R, I went this way. Right? I went line, line, line. But now that I have those lines, all of them in the table, I'm going backwards to compute x and y. So there is a formula for how to get this x and y. We say this value has to move here. So whatever value we had the coefficient here, we're going to put it here. And then we can figure out what we need. How much we need in here. In here, what do we have? 51 times some value plus 9 times some value has to be 3. So if I get the 51 to put it here, the minus 1, what do I need in here? So the formula is the x k, if you like. This is k equal 1, 2, and 3, right? Xk is the next y, so that will be y, k plus 1. And the yk, this guy, what I have here is, let me see, that's the previous x minus the coefficients times the previous one. That's what I have. The quotient at this line. So the quotient at line k. K plus 1 maybe? This is k plus 1. Let's check this formula to see if it works. So this is how I got it, right? I moved the next y into the x position. Are you guys follow me? This is simple arithmetics. I didn't get anywhere yet with that essay. I'm just recapping 7th grade arithmetics, okay? That nice. This formula works. So like for this line, who's yk that we've got? Minus 1, right? Would be xk plus 1 is who? 0 minus the quotient at this line, 1 times yk plus 1. The y at the next line. Is that working? Is that coming out correct? Yeah? How about this one here? Again, the x moving there, that's easy. I just do this minus 1, I put it here. But what's happening with the y? So y, if I do this line, y1, that would be 6. It's coming out as the next x, which is 1, minus the quotient at this line, 5, times the previous, the next. Is that checking out? So this is kind of the formulas that allow me to move the x's from k plus 1 line back to k line. So that is our Euclid extended algorithm. It not just finds the GCD, that will be the simple Euclid, not extended, because I don't have to go back to these lines. If I just go this way, few steps, I'll end up with r equals 0. I know I got my GCD. But if I now, having the table go backwards with x and y, the last x and y again are trivial, 0, 1 all the time. But then I apply this formula to get x and y back. I get the coefficients all the way to the first line. The coefficients that I need are minus 1 and 6. Again, these are not unique. There are many ways to do them, and some other way will produce different coefficients. That's fine. Okay? So this is an algorithm that can be implemented quite fast in practice, even for large numbers. Even these A and B are very, very large. If I use this method, I'll have a problem with the factorization. The numbers we're talking about, they have 1,000 digits. So they 10 to 1,000 or 2 to 1,000. Like in here, 2048 bit encryption, because the numbers are astronomically high. So it's not easy to get the factors out for GCD or for some other purposes. But this algorithm I can still implement if the numbers are 1,000 digits long. The reason that is that every time I move from a line to a line, every time I do a division, I make exponential progress. I only need a logarithm number of steps to get there. So if my number is really 10 to the 2,000, it's a huge number, right? I can't really do any interesting operations with this number, even with a computer. How many steps will take, and that's A and there's another B, right? I get two of them. How many steps will take to find the GCD? Logarithm, which will be roughly 2,000. Any algorithm that's linear in these numbers is too slow because the 10 to the 2,000 is a very big number. But any algorithm that's logarithmic, it's okay. 2,000 steps will not be a big deal. So GCD can be implemented efficiently, and then I can get this to work even for very large numbers. Okay. So that's good. We still have preliminary. We've got GCD, we've got prime numbers, and now the other thing that we need is the, we're gonna talk a little bit about these coprimes. Where are they? We said coprimes, they have no thing in common, right? So, let's put it here. So I'm particularly focused on coprimes now, A and B. That means the GCD of A and B equal 1. And according to this formula, that means there is an x and y integers, right? With property what? AX plus BY equal the GCD, which is 1. So this is the main thing with coprimes. They have no prime factors. That means if you apply this theorem here, you get an x and y such that you get a 1 bilinear combination. And you can see why the easy part of this theorem is to see it that way. If there is an x and y with this property, it's very easy to show there's no common factor. Why? So this way the theorem is not that easy. But this other way, if this is happening, they cannot have a common factor. If A and B would have a common factor, say 5, 5 divides A, 5 divides B, it will divide any linear combination of A and B for any x and y integers, right? Because if this is a multiple of 5 and that's a multiple of 5, the whole thing will be a multiple of 5, which is impossible because 1 is not a multiple of 5, right? So the easy way to see this theorem working is the other way, right? Anything that have a p prime factor, A and B, will have a, say, 2 or 5 or 7 or 11 in common. That will be a common factor for the whole expression, right? If P divides A and P divides B, then P divides AX, then P divides BY, which means P divides their sum, which means P divides 1. So that's a contradiction. Assume P common factor. These divides, I don't know if you remember, it's simply saying P divides A, it's equivalent to say A is P times some K. So we say P is a divisor of A, or A is a multiple of P. That's what we do, right? So the other way, it's not that easy to prove. Only right to left is very, very easy. Left to right, we don't have time to do it in class, but we can prove it either with this equation here or with some other methods that this is happening. So what I want to show you is a little bit of magic that this is not come out as a second grade or high school, okay? Secondary school. It's gonna come out as pure magic. So far, I think we're all on the same page, but now we're not gonna be on the same page. So here's the magic that I have in mind. If I pick an n, let's pick an n, a nice n, 15. I'm going to say the Zn is 0, 1, 2, up to 14. That's the reminder set. Sometimes people say Zn star excluding 0. If you see this notation, they mean without 0, 1, 2, 3, up to 14. But I'm going to introduce another set, which is Cn. It's included in Zn star is the set of coprimes, or relatively prime. So what numbers in this set are relatively prime with who? With 15. So what's that set? Who is relatively prime? Say 1 is there, obviously, because 1 cannot have a common prime with 15. Who else? 2. 3 is there? No, because 3 is a common prime between 3 and 15, so 3 is missing. 4, 5, no, 6, no, 7, 8, 9, why not? 3 is in common, right? Between 9 and 15. So 9 is not 10, why not? Who else? 12, 13, 14. So this set is magic. Set of coprimes. The size of this set is how many? 8, right? So there's some very, very interesting properties of this set, which are putting the base or what we call number theory, not just for cryptography, for anything. All the number theory relies at the base on this set. So we'll do 2 or 3 of those things, and once we do them, RSA is a very simple mechanism once you understand how this set works. So number 1 property is that if n is 15, which decomposition into prime is 3 times 5, then the size of Cn, how many things are in there, I take the primes minus 1. 3 minus 1 times 5 minus 1. So what if n is 3 squared times 5 times 7 squared? Who's going to be the size of Cn? How many coprimes are in that set? I have to expand that formula, right? I don't think I have it here. I think it's something like 3 times 3 minus 1 times 5 minus 1 times 7 minus 1, I think. Not sure. I can check it out. So once you have the decomposition of n, you can tell immediately how many coprimes are how many reminders. This is all included in the reminder set. How many of them are coprime reminders, meaning relatively prime, no common factors. Right? So that's one thing. The other thing that's important about this is this size of C of n, we call it, we have a notation for it. Let me do it here. size of C of n, we call it phi n. That's just a notation, and this is 8 in here. So this will be phi of, let's say phi of n, like a function, phi of n. This phi will be phi of 15, right? And this will be here, phi of, how much is 3 squared times 5 times 7 squared? Anybody knows? 3 times 7, 21. Squared is 441 times 5, 2, 2, 0, 1. Right? 205. So I can I have this phi that's called an Euler function or Euler number. He's the one who thought first about those problems like 250 years ago. And I know how to compute phi just by doing the composition into primes. Now, here's another thing. If I pick any value in the Cn set, I'm going to compute this. So, for example, let's say, let me write this here down. Let's say n equals 15. I pick A in the Cn set, for example. So n is fixed here. A, let's say I pick, I have to pick something from this set, the coprimes. Let's say I pick 4. Let's pick 2, maybe easier. If you look at this set, powers of A, modulo n, that's going to be the set of 2, 2 to the 2, 2 to the 3, so on and so forth, right? That's what we mean the powers. Of course, taking modulo after every operation, right? So what is this set in reality, if I really take those powers? 2 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16 modulo 15, 1. And now what's going to happen if I do the next power? 2 to the 5th. So this is 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4 modulo 15. What's the next power? 2 to the 5th. But that's going to be just 2 multiplied with the previous one, which will be 2 again, then 4, 8, 1, 2, 4, 8, 1, so on and so forth. So this set is really only 2, 4, 8, and 1. That's it. It's, of course, we expect those things to repeat, because in Zn, in the reminder set, everything must repeat. There's only so many reminders, for 15 reminders. So if I write an infinite sequence, it's got to repeat itself. There's no way to produce different values. But this is far more interesting than just that. It's not just repeating. It's repeating certain things. Like if I look at these coprimes, I notice that if A is a coprime, all those powers are going to be in coprime set. Right? Even though the set of reminders includes 15 things, if you look at those powers, they are from the coprime set. That's easy to see. If A has no common factor with n, neither A to some power will have a common factors, because common factors cannot appear out of the blue. If A didn't have a common factor with n, how can A at some power has a common factor with n? A only has the factors, A to the any power has only the factors that A has. So if there was no common factor, right? So what I'm saying here is that if GCD of A and N is 1, the coprime, that means GCD of A at any power and N is also 1. Because A times A times A times A cannot suddenly get a common factor with N, right? What are the N factors? 3 and 5, right? Because N is 15. If A doesn't have a 3 or a 5 in it, neither A at any power will somehow get a 3 or a 5, because the A at the power has only the prime factors that are in A. Now, there's a lot more of them, right? If there will be a 3 at power k equal 100, now there's 100 3's. But if there was no 3 or 5 to begin with, there won't be one now. So that's why this P of A must be also included in the coprime set. Since A was coprime, the powers of A are all also coprimes. So P of A has only coprimes. And the last thing that we need here, that it's something for you guys to take home and prove, is that P of A with the operation that's modulo multiplication forms a subgroup of C of N with the same operation, multiplication. Now I know some of you don't know what groups and subgroups are, that have to do with high-level algebra. But some of you, I think, did groups when you were in high school, right? High topology algebra, rings and corps and groups and properties like that. Those are not, there's fancy names, but the manipulations of those things are each quite easy. What it's saying is that there are some rules for how a group works. It has a neutral element. If you add 2 things or multiply 2 things, in this case, you obtain another element of that group. This is saying this forms a subgroup. Okay? So we don't have time to explain what a subgroup is, but there's a simple mechanism that says within P of A, everything is contained. In other words, if I do multiplications of those numbers, I'm not getting out of this set. So if you multiply any of them, 4 times 8, 32, modulo 15 is 2, right? 8 times 8, 64, modulo 15 is 4. So everywhere you multiply those things, you're going to stay within P of A. That's the notion of subgroup. So there is a major theorem about subgroups, which says P of A, the size of the subgroup, divides the size of the group. So the number of elements in P of A is a divisor of the number of elements in C of N. That's true for any subgroup of any kind. The size of a subgroup has to be a factor of the size of the group. So if the group has size 100, any group, a subgroup could not have the size 40. Why is that? 40 is not a factor of 100. So if I have a group of size 100, I can have subgroups of size 5 or 10 or 20 or 25, right? Or something like that, 50 maybe, but not things that are not. That's a very simple theorem. It's just how the structure of the groups and subgroups work, right? So that's called Lagrange theorem. These names, Eulers and Lagrange, are huge names. So this is a critical part for number theory, because This C of n, we already know who's the size of C of n, right? We said earlier, someone, what's the size? We're gonna call it phi of n, right? That's the size. The number of coprimes, so for 15, how many I've got? 8. P of A though, we didn't think yet about who's the size of this P of A. So, mechanically speaking, when did we finish P of A? We started with some A, right, 2, and then we do 2 times 2, 4, 2 times 4, 8, 8 times 2, At what point we said, okay, we're done? When we saw? 1. Why is that? Why are we done? Because if you see 1, if you keep multiplying by 2, you're going to see the same values again. So there's no new value after 1. There will be again 2, 4, 8, 1. So we stopped when we've got 1. So in other words, we could say, who's the size of P of A? This is some number K. In our case, K was how many? 4. With the property that the last one is actually, so how do I write that? A at power K equal 1 modulo n, right? That's when we stop. We multiply A with itself, A squared, A third, A fourth, A fifth, so on and so forth, until we solve power K. That gives me 1, right? This one here. So how many elements are in here? Well, are that power K. If we stop, this is again 2 to the 1, 2 to the 3, 2 to the 1, 2, 3, and 4. We stop here at 2 to the 4. That means the size of the set is 4. So this K, it's called the order of A. It's like the number, the exponent that you need, so that A to the power of that order. So A at the power order of A is equal 1 modulo. Every coprime has an order. Like we pick 2. But what happens if we pick 4? Who's going to be the power set of A? 4. 16 is? So who's the order of 4? 2, because at power 2 I got 1. I'm always going to get 1 eventually, if I start with a coprime. If I start with a non-coprime, for example 3 or 6, I will never get 1, because 3 at the power cannot give me 1. 3 is a common factor with 15. At any power, 3 is still going to be there. I can't get 1 because 1 has no prime factors with 15. How many people follow me here? Hands up. Okay. So let's rewind it and have some questions now. I'm going fast, of course, because some of this stuff is easy and some of it has been seen in previous years, modulo operations and stuff like that. Now I know this is maybe new with the subgroups and the powers. So let's pick another one. Say A equal, let's pick another coprime there, 7. Who's PA? 7 times 7? 49 is what modulo 15? 4. 4 times 7? Modulo 15? How much? 13. 13 times 7? 91. Modulo 15? 1. So the order of 7 is 4. Okay, let's pick one more, last one, 14. How much is 14 times 14? 196 modulo 15? 1. So the order of 14 is what? The reason this is actually very easy to see. It's 1. Instead of thinking of it as 14, modulo 15, I can think of minus 14. It's hard to think about, but if I think of it as minus 1, modulo 15, 14 is the same as minus 1. Minus 1 times minus 1? 1, right? That's easy. So modulo 15, you always want to pick the remainder. That's the easiest to think of. So see how those orders always come out as dividers of the order of Cn, which is how many things are in Cn? 8 things, right? So any one of these orders will be a divisor of 8, 2 or 4. And there's no one that's 8, but sometimes there could be 8, right? So the theorem that says PA divides Cn, that's a central theorem in mathematics in a lot of fields. It comes from subgroup theory, but applied here means that. That means if C of n is it's a multiple of PA, that means C phi of n, right? The size of the coprimes, it's size of PA times something. That's what it means. This is a divider of that. It's P of A times some value, right? Then we can rewrite that and say phi of n. P of A, it's the order of A, the size. By definition, we stop P of A when we reach 1, that K, so we reach 1 when we exactly have the order, times something. So now, if I do the following equation, I take that A and I raise it at the power phi of n. I want to compute this value. A at the power phi of n. I say that's A at order of A times something, because phi of n is order of A times something. But how much is A at order of A by definition? Order of A is the power K, such that A at that power gives you 1. So A at order of A, everything at some power, which gotta be 1. How did I get here? I say, take any one of these A's that's coprime. Raise it at the power phi of n. Phi of n in my case for this n will be what? How much is phi of 15? 8. Again, that was the size of the coprime set. If I look at this equation, because of the Lagrange theorem here, phi of n, it's always the order of A multiplied with something. But A at the order of A, by definition, is 1. Because that's what order means. It's what power do you need to get a 1. And then once I have 1 at anything, that's going to be a 1.
We are talking about modular here.
Everything is modular. Modulo 15. In modular arithmetics, everything is modular. So that's a very important theorem. That's called the Euler's theorem. Euler's theorem. Again, what this is saying, it's saying we still have this. I want to take very quickly another example of this. So we did 15. But let's take some other example. How about we take, let me do that example here somewhere. Board here. So I want to take n 3 times maybe 2 times 5 times 7. How much is that? 7 70. So who's phi of n? 1 times 4, 24. That says there are 24 coprimes. Well, let's see. Are there? Cn. What are the coprimes with 70? 1. Is 2 a coprime? No. 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, 15, 17, 19, 21, 23, 25, no, 27, yes or no, 27. 3 times 3 times 3, that's 27, and 3 is not common to 70, okay? 29, 31, 33, 35, 37, 39, 41, 43, 45, no, 47, 49, no, 51, 53, 55, no, 57, 59, 61, 63, no, 65, 7 times 9 is 63, right? 65, no, 67, 69. So how many we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 2, 3, 4. Works, right? We got 24. That's like the theorem says, you should get 24. So now if I pick a coprime, A is coprime with 70. So I can pick one of these. This is the coprime set. Say I pick 9. What is the set of powers of A? The first one is 9, obviously. Then 9 times 9, modulo 70, 11. 11 times 7, times 9, sorry. 99 modulo 70, 29. 29 times 9, 261 modulo 70. Are you sure? 51? I don't know. 51 times 9? 459 modulo 70. 39, I think. 39 times 9? 351 modulo 70. So how many things are in there? 6. Size of P of A is order of A, which is 6. And no surprise, this 6 is a factor of 24. That's what this theorem here was saying, that the size of that P of A as a subgroup, which is 6 values, that's a factor of how many coprimes are there to start with. That's why we have this theorem. if I am to raise that a equal 9 at power 24, so to repeat this theorem, a at phi of n is a at 24. I could just write a at 6, everything at 4, but a at 6 is 1. So it's 1. So it's going to be 1 for every single coprime. Nice. Now we can do RSA. We needed this preliminary number theory to do RSA. But RSA is not hard once you know all this stuff. So how do we do RSA? So RSA has two parts: the setting up of the protocol before you use it, and then the actual use it. How do you encrypt and decrypt things, right? So RSA setup or protocol, that has to do with what you need, you as the master, what do you need to set up for encryption, decryption to work. And then there is RSA usage. Once we have the protocol, how do we actually encrypt and decrypt things? So here's the setup. P and Q are very large prime numbers. N is P times Q. And N is public. N is public, not P and Q. Those P and Q are secret. But the product is public. So if this is P is, I'll take an example in a second. If it's 7 times 11, those P and Q are secret, but their product, N77, it's what I make public. So now I have phi of n, which I know how to compute. If n is a product of two factors, who's going to be phi of n? There is a formula that works in general. So what's the p minus 1 times 2 minus 1? E, it's called the encryption key. Usually a prime. It doesn't have to be a prime, but it's a prime number. D, this E is public. So N is public, and E is public, the encryption key. The encryption, if I have a message, we call it message, but it's really a number. That's what we mean, a number. A message X gets encrypted as Y equal X to the E modulo N. So the encryption is taking whatever you have. It's a number because everything gets transformed into numbers. Whether it's text or images and stuff, for computers, everything is numbers. So I take that number X, how do I encrypt it? I raise it at the power E modulo N. And the decryption, that's a secret key. The decryption must have a property. E times D has to be 1 modulo phi of n. Not modulo n, modulo phi of n. Which is the same as saying, in plain words, E times D is phi of n times something plus 1. That's what it means to be 1. It's the phi of, it's a multiple of phi of n plus 1. So you need to find this D. as part of the protocol, but that's secret. Okay? How the decryption goes? This Y, this message X, it's called plain message. That's what I want to encrypt. And Y, it's called a cipher. What's already encrypted. So now I have to reverse that operation. I say, okay, if you give me a cipher, I think it's too high. Cipher Y, how do I decrypt? I do X, which is getting back the original message. It's Y at D, sorry. Modulo N. So it's the same kind of operation. One raises the message at power E, takes modulo N. The other one takes the cipher, raises at power D, and takes modulo N. Of course, E is public, N is public, so everyone can do this operation. Raising at power E, taking modulo, everyone can do it because everyone has E and N. But the other way, you need D, and D, only the people who are authorized to decrypt, they will have the private key D. Now, the question, mathematical question, is does it really work? Are we gonna get back the original message or not, right? So before we get into how to do it, why is this getting back the original message? Why is this X obtained here is the same X that has been done there, right? So why is that working? That's based on what we've discussed so far. That's easy to see. If I take X at E modulo N, that's the encryption part. I got Y. What's going to happen when I do the decryption? I raise Y at power D modulo N, right? That's this decrypting operation here. Well, what's that going to give me? Who's Y? It's X at power E, because Y, that's how I encrypted it. Now at power D modulo N. So that's X at ED, right? Modulo N. But ED, there's a mathematical condition there, phi of N times something, right? So ED were set up that way. Notice that this property does not depend on X. The fact that E times D have a certain property with respect to N, it's independent of how I pick my message X. There's nothing to do with X. So this is X at phi of N times something plus 1, right? But what is Euler's theorem? It tells me about X at phi of N. We're saying every coprime raised at phi of N is going to be, what was that theorem? There was somewhere here. Any coprime A raised at the power phi of N is 1. So this part here must be 1. So this is, let's decompose this plus 1 on the side. So this is X at phi of N times something, times, instead of plus 1 at the exponent, I write X down. So the Euler's theorem says that X of phi of N must be 1. So this is X, 1 at something, times X, so that is X. That's the mathematical guarantee that if I did this correctly, I'm getting back the original X. Relies on the fact that I pick E and D such that when I do encryption and decryption one after the other, I get phi of N in here. And Euler's theorem tells me anything at power phi of N will be 1. So then the plus 1 just guarantees to give me back the X. That's it. Now, this theorem doesn't work for any A, or it's only for coprimes. So there's a legitimate question to say, wait a minute, X gotta be any message, right? When you encrypt, decrypt. And even though I don't control the E and D, what happens if somebody picks an X that's not coprime with N? It won't work, right? But that's very unlikely for somebody in practice, once I set up the protocol, to pick an X that's not coprime. The reason for that is that P and Q are very large prime numbers. X are more like normal things, like how much money you have, or what's your name, or what's your password, or what's the ASCII code. Those X are usually practical values, right? My point is that any reasonably small value, like the number of colors or pixels of money or whatever, it's gonna be small enough. Think about if N is P times Q, what is the first reminder that's not coprime? So in the 15, we have it here, right? Was 3 times 5, right? 15. This is all the reminders. Except 0, what's the first one that's missing, that's not a coprime? 3. Why do you think that's 3 coming from? It's a factor, right? Everything smaller than the 2 factors, P and Q, everything 1, 2, 3, 4, 5, up to P minus 1 or Q minus 1, those will be coprimes. If P is a big number, like 10 to the 2000, and Q is also a big number, like 10 to the 2000, everything up to P minus 1 or Q minus 1 are going to be coprimes. And in practice, the values people use to encrypt, even if you think, okay, that's in the millions or billions, that is still a lot smaller than 10 to the 2000. 10 to the 2000 has 2000 digits, while a billion has only 9 digits. So for any practical purpose, as long as if X is smaller than P and smaller than Q, it's guaranteed to be coprime with N, which is P times Q, so this whole thing would work. Now, if somebody picks a number that's very, very large, there is a small chance to hit P or Q, and then the theorem would not work. But even then, it's a small chance. P times Q, the only numbers that are missing here in the coprime set are multiples of P or Q, right? Because to be a non-coprime, you have to have a common prime factor. And the only common prime factors are P and Q. So what's missing here is P or Q, right? And even if you pick a large number X, there is a very big chance that you pick a coprime because there's a lot of coprimes in there. Okay? So that's how it works. So let's take an example. If I use it, I already set it up. I have it. That's the usage. Let's say the protocol is set up with P equals 7, Q equal, I don't know, 13. Right? N would be 91, the product. 7 times 13, 91. And phi of N will be 6 times 12, 72. Remember this formula P minus 1 times Q minus 1. It's only correct when N is P times Q. If it's a different decomposition of prime factors, phi of N still exists, it's just not P. There's a general formula, but it is that formula in this case. So now, how do I encrypt things? I have to set up E first. So E is, for example, I need to pick D, E, and D such that E times D is is 1 modulo phi of N. That means P times D minus 1 has to be phi of N 72 times something. We could say D has to be the inverse of E modulo means the same thing. If two numbers, the product gives me 1, in modulo arithmetic, we call 1 the inverse of the other. That's just a definition. There's no additional stuff. It's just D is the inverse of E modulo phi of n. So if I set up E equal 5, pick a small prime number, I need now D to be the number that if I multiply with 5 to give me 1 modulo what? 72. So what number multiplies with 5 gives me 1 modulo 72. So this is 5 at minus 1, the inverse modulo 72. Now that's an integer, even though it reads like funny, like 5 at minus 1. We really mean modulo arithmetic. So it's whatever integer gives me, anybody knows which one I need? 5 times what? How can I compute this inverse? So now I can guess it, right? Suppose I guess it to be, it's going to be a coprime with 72, right? The inverse cannot be 36 because 36, it's not coprime. This has to be, both E and D have to be coprime with 72. So I could guess 13. 13 times 5, 65. Is that modulo 1? Modulo 72 gives me 1? No. I could guess another one. I could guess 19. 5 times 19? 95 modulo 72? 23? No good. So I can keep guessing, or I can build a power set. If I want to get the inverse, I can build a power set. How do I know what this is? Well, I can build the power set P E. So what is that going to be? 5 is the first one. Next one is 5 times 5, 25. The next one is 125 modulo, this is what? How much? 53. The next one is 5 times 53, 265 modulo 72. Out of 265, 49. And I can, the moment I see 5 at k equal 1 here, where is my inverse? Where is my 5 at minus 1? No, k is the order. Who is the inverse? 5 at minus 1, the inverse, will be 5 at what power? 5 at k is 1. So what power I need to multiply with 5 to get 1? K minus 1, right? The previous power, the one right before it, that's the inverse. Because 5 at k minus 1 times another 5 gives me 1, so that's the inverse. So I could build this power set, and I know I'm going to get 1 at some point. And the previous power's got to be the inverse. Or I can do Euclid, right? Yeah. If I do extended Euclid, I'm going to get what? What does it give me? It gives me the GCD. GCD is going to be 1, right? GCD equal 1. It's going to be A. Who's A? A in this case is 5 times x plus A is going to be 72. 72 times x plus B is going to be 5 times 1. So if I apply extended Euclid on 72 and 5, I'm going to get the two coefficients, right? Who's the inverse now? If I get 1 equals 72 times x plus 5 times y, I say y is the inverse. Is that true? How much is 5 times y modulo 72? 1. So y is the inverse. If that happens, then 5 times y modulo 72, it's going to be, I look at this 5y as 1 minus 72x, 1 minus 72x modulo 72, which is, of course, 72x modulo 72 is 0. So that's 1. So it means y is the inverse of 5. So that's why we did the GCD extended, because I can apply it here. I don't know who the inverse is. I can apply the GCD for 72 and 5. And if I get the coefficients, the coefficient for 5 is the actual inverse. Now we can do that. We can do the Euclid, or you guys can guess what the inverse is. Anybody has a guess or what the inverse of 5 modulo 72 is? The way we check it, we multiply 5 with that value, and if we get 1 modulo 72, that's our inverse, right? It's 29. 5 times 29 is?
145.
145 modulo 72. 72 times 2 is 144. So that's 1. But either checking the power set or doing the extended Euclid, I would have gotten the 29. So now that I have this protocol, that's again the protocol. The usage is what? If somebody has an X that's a message, for example, 19, how do I encrypt? Y is 19 at the power 5 modulo 72. So I don't know how much that is. 19 at power 5 modulo 72. If you guys can do that with a calculator. And then if I want to decrypt, this is encrypt. The decrypt is, I'm going to take this value y that you guys are computing, right? Y 19 at power 5 modulo 72. Anybody got an answer? Huh? 19 at power 5 modulo 72? How much is it?
19.
19.
That's a better example then. Is it 19?
Yes.
Unfortunately, 5 and 19 play out this. What happened? The problem with 19 is that the order of 19 is 4. So if I multiply 4 times 19 times 19 times 19 times 19, I get 1. So one more time, I get 19. Right? Let's try a different example. This is no good. Let's try 13. 13 at power 5 is what? It's also 13? 13 at power 5 modulo 72. I mean, it's not like it won't work. That example work is just encrypting the message with its own value. It's not what we want to do. 11? Yeah? So then backwards, if y is 11, 11 at the power 29, modulo 72, we don't want to, if we want to really do this calculation, we're not going to do 11 at 29. That's a big number, right? So how do we actually do 11 at 29? If I want to do that calculation procedurally, like with a computer, I'm not going to do 11 at 29. I'm going to do repeated squaring, right? So 11 at 29 is what modulo 72. I do 11 at 2 is what? 121, which is modulo 72. 49. And then I do 11 at 4 is 49 squared, which is what? 49 squared. 2, which is how much modulo 72? Everything is modulo 72. 2401 modulo 72?
25.
25. And then I do 11 at 8, which is 25 squared. 6, 25? No. Is that true? 625. Modulo 72? So I need to know enough powers. 11 at 29 is probably 11 at 16 times 11 at 8, right? Times 11 at 4 times 11, right? So I may need one more here, 11 at 16, but this is repeating. This is going to be 49 squared, which I've already computed. So this is 25. So this might be 25 times 11 at 8, 49 times 11 at 4, 25. 11 at 1 times 11. So that's how I can get 11 at 29.72 with repeated squaring faster than just raising the power. And it's essential not just to do repeated squaring, it's essential to take modulos quickly so the numbers don't get too big. Right? I could raise to a big power this way, even though the number itself would be way out of the bounds what computers can do. By taking modulos early on, I keep it within range, so I can do the operations with it. Okay, so that's how RSA works. I have one more question to discuss, which is, wait a minute, how do we get large prime numbers to start with? Right? This whole thing works. Like, we can compute phi of n quickly. We can then increase messages. Again, this mishap we have here with 19, it's only because the P and Q we had are too small. If we really picked large P and Q, we wouldn't have 19 modulo that equals 19, you know. That only happened because the example had P and Q small numbers. But how do I pick big P and Q? If I really want numbers with 2,000 or 4,000 digits, how do I know they're prime numbers? I can enumerate prime numbers, right? 2, 3, 5, 7, 11, 13, 17. That will take a long time to get to 10 to the 2,000. Because for every prime number, I have to check if it's prime. We already said factorization is a very hard problem, right? So if I pick the next number and factorization's hard problem, how am I going to know it's prime or not? This is hard to do. Again, we are assuming that factorization is a hard thing. So the idea of taking a very large number and factorize it, we know or we believe that that's going to be hard. So we can't do that. We can't take a large number of 2,000 digits and factorize it. But how can you check primality? So the idea is, okay, you cannot factorize it or we cannot factorize it. It's too large. But can we check primality without factorization? Obviously, the other way it's easy. If you have the factorization, you know if it's prime or not. If it's only one factor there, it's prime. But the other way, can you check primality of a large number without actually factorizing it? The answer is yes. But this has been a problem going on for hundreds of years. And only very recently, like about 10 years ago, somebody wrote a polynomial time algorithm that deterministically not factorizes, but determines primality within polynomial time, that is within the 2000, the exponent, the logarithmic time, without explicitly computing the factors. But that's more like a theoretical result. You know what people do in practice? in practice, even the RSA people, they use this. So here's primality test for large P. So I have a large P number, and I don't know if it's prime. Well, I'm computing tentative phi of P. That is tentative, assuming it's prime. I don't know if it's prime or not. But if it be prime, whose phi? How many numbers are co-prime with the prime numbers? That's very easy, right? If P is 7, what are the co-primes with 7? Huh? Everything except 0. So that supposedly is just P minus 1. That's actually coming from the formula too. If you apply this Euler formula for how many co-primes you have. So if P is 13, the co-primes are all the reminders except 0. Right? So it's minus 1. But I say tentative because I'm not really sure it's prime or not. Right? So then here's what I do. Primality test. Pick some A between 1 and P minus 1. This is supposed to be a co-prime with P, assuming P is prime. And test this theorem. Is A at power P minus 1, because phi of P is P minus 1. Is that equal with 1? Okay. That's what the theorem says, has to be equal with 1. Modulo P. So if we get the answer no, if the answer to that is no, what do I know for sure? So my logic was, if P was a prime number, phi of n would be P at minus 1. Theorem says any coprime at that power has to be 1. So if I don't get 1, P is not prime. But if I get yes, maybe. So if I get yes, how do I improve my chances to get a prime number? Try another A. Try another. So if I try enough A's, maybe 20 A's. This is actually, again, with repeated factorization, with repeated squaring, I can test this very, very quickly, even for large numbers. So I can try one A, another A, another A, another A. And if all of them succeed, if all of them says 1, 1, 1, 1, I say, maybe it's prime, right? Is there, theoretically speaking, a way to succeed all the time, but not be prime? Like for every single A, you get 1, 1, 1, 1, and yet the number is not prime? Yes, that's possible. There's a famous guy, Carmichael, who figured out those numbers, but they're so rare that we don't mind something. Every once in a while we get a prime that we think it's prime, but it's really not a prime. So this is a very efficient primality test. Try a bunch of A's. The chance increases exponentially. If you try 10 A's, the chance, if all of them says yes, the chance of not having a prime number is 1 over 2 to the 10. So it becomes very accurate. If he passes 20 A's, the chance of not being prime is 1 in a million. If he passes 40 A's, the chance is 1 in like a trillion. Okay? So it's not for sure. I will never be able to say surely it's prime, but I'll say with very high probability I got myself a prime number. So that's how we generate primes. We generate randomly a big number with many digits. We apply primality test, and if it says not prime, that's for sure it's not a prime. But if it says, okay, pass the test, with high chance it's prime. Okay? So that is the shortest version of RSA I can come up with. And RSA is a quite practical system, both for theoretical purposes, because the theory is very easy. It's all iterative. But also the implementation is very easy. And you cannot do it the fact that it's verifiable. People could verify the protocols to make sure they work. Now remember a few years ago, there was this issue with NSA tracking cryptography, being able to break into cryptographic systems, and some people naively asked, maybe they broke up factorization, right? I mean, NSA is so smart, right? Maybe they figured out how to factorize prime numbers and they can break into any cryptographic systems. No. The mathematicians came the next day and say, don't worry, NSA doesn't know how to factorize prime numbers. That's no way. What happened? They tweaked the protocol. They had a back hand in the setup. If I set up this protocol, which is a software embedded in a chip somewhere, right? Every time the protocol does what it does, maybe it sends me, what do I need? If I want to be the master of all decryptions, I could get D, but the really good ones to have are P and Q. Because P and Q will allow me to get everything out of it. So if I set up a protocol that says every time somebody says, give me a new P and Q, set up RSA, set up my key, blah, 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 send me a quick email with his email address and P and Q. Right? That's not breaking the mathematics. That's just having a backdoor into the system. That's what NSA did. They had a backdoor into it. They didn't break the math of RSA. Okay? Office hours this week, of course. We have an exam on Saturday. So I would start focusing on that exam. I'm not picky on the deadlines. Whatever the website says in terms of the homework deadlines is not relevant as long as the TAs can grade it. So you should talk to the TAs to see what time they have. If they grade it by the end of next week, which is when I have to put the grades, the last few homeworks, 11, 12, 13, won't be penalized as late. Again, with the condition that TAs can actually grade it. So if you're still working on 11 or on 12, that's fine. Just make sure the TAs can grade it.